Hey everyone, today we're going to be going over three really interesting number theory puzzles that don't require too much special math knowledge, but require a lot of creative thinking and thinking outside the box instead. So we're going to start with our first puzzle, which is about opening 1600 lockers, and I'm going to put it right there. So it says there's 1600 closed lockers in a high school with 1600 students. So I'll let these lockers be 1, 2, 3, 4, 5, 6, and so on. And it says we start with student 1 opening all 1600 lockers, then student 2 closes lockers 2, 4, 6, 8, 10 for the even numbers. Then student 3 changes the state, which is opening the lockers that are closed, or closing the lockers that are opened, for multiples of 3 lockers, 3, 6, 9, 12, 15. And then student 4 does the same for multiples of 4 lockers, 4, 8, 12, 16, and so on. And this goes on until all 1600 students has had a turn. And it's asking us to find how many lockers are going to be open. So let's start off by thinking about what student 1, 2, 3, and 4 are going to do. So student 1 opens all 1600 lockers. I'll denote this by just putting check marks under each. And so on. I'm not going to draw out all 1600 check marks. So after that, student 2 closes lockers 2, 4, 6, 8, 10. And I'll just put a check mark below this too, because this opening check mark and this closing check mark are going to cancel each other out. Then after that, student 3 changes the state, opening the closed lockers or closing the open lockers of multiples of 3. So I'll put a check mark here, which means student 3 closes the open number 3 locker, and put a check mark here, which means student 3 opens the closed number 6 locker. And then student 4 does the same for 4, 8, 12. So at this point, student 1 has opened every locker. Student 2 has closed every locker that's a multiple of 2. Student 3 has changed the state of every locker that's a multiple of 3. And the same thing for student 4. Now, we can try thinking about this from the perspective of a locker, not from the perspective of each student. So let's think about locker 4, for example. We can notice that the students who open or close locker 4 are either student 1, student 2, or student 4. And any student greater than that won't be changing locker 4 at all, because they'll be starting from a number that's greater than 4 and won't be going back. So we see that the students who open or close locker 4 are going to be students 1, 2, and 4. So now let's also look at which students are going to be opening or closing locker 6. So we have here that students 1, 2, 3 will be. Four won't be because 4 then 8 skips over 6. 5 won't be because 5 then 10 skips over 6. And then student 6 will be starting with locker 6. So we also have student 6 here. And what we can notice is that for some locker n, let's say, so here we have n equals 4 and n equals 6. We notice that the students s who open locker n are the numbers s, so that s is a divisor of n, which we'll denote by s long bar n. And we can see that this is true here because 1, 2, 4, I'll divide locker number 4. And 1, 2, 3, 6, I'll divide locker number 6. And I think it's clear to see why this is true from the definition of which students are going to be opening which lockers. Because student S is going to be opening all lockers such that the locker is a multiple of his or her number, then the lockers are going to be opened by exactly which student's numbers divide the locker number. So with this in mind, all we need to do is figure out which lockers are going to be open at the end. But to figure this out, we just need to see how many lockers are opened or closed an odd number of times, because doing so an even number of times would just leave it closed since each opening is cancelled out by a closing, but an odd number of times will leave it with an opening. So to do this, we'll use our formula for the number of divisors of a number, n, which is, if we let it be p1 to the a1, p2 to the a2, and so on for prime numbers p, then this is going to be a1 plus 1 times a2 plus 1 times, I guess, a3 plus 1, a4 plus 1, however many number of prime number factors it has. Let's just say it has k prime factors, so a k plus 1. And this is true because of our formula for the number of divisors. So now let's think out what it means for this number to be odd. So we know that any odd number times an odd number will be odd. Let's just say O times O equals O. But then anything times an even number is going to be even. So O times E equals E, and E times E equals E. And this is true because if you have a number with a factor of 2, let's say 2k, and then you multiply it by anything, like let's say y, then we're going to have 2ky, which is even because that's a factor of 2. So now that we know that any number times an even number will be even, we know that none of these numbers can be even. Because if any of the factors are even, then multiplying it with any other factor will leave it to an even number. Then doing that repeatedly will still leave you with an even number. So we know that all of these a1 plus 1, a2 plus 1 through ak plus 1 are all going to be odd. So let me just say ai for any I plus 1 will be an odd number. So we can say an odd number is 2c plus 1, since an odd number is always 1 more than an even number, which will be 2c. And this means that ai is going to be equal to 2c for some even number 2c. And what exactly this means is that all of these ai's, a1, a2s through ak, these will all be multiples of 2. And this means that all of these factors are going to be square numbers, because any p to the 2c will equal p to the c squared. And then multiplying all of these together will also leave you with a square number. So what this means is that any locker that's a square number will be open at the end, and any locker that's not a square number at the end will not be open at the end. So we just need to find the number of square numbers between 1 and 1600. So clearly 1 is a square number, 2 and 3 aren't, 4 is a square number, 9 is, and so on. So ending at 1600, we can actually notice that this is 40 squared, which means we have all the all the square numbers from 1 squared, 2 squared, 3 squared, all the way up to 40. Which means our answer is 40 lockers will be open at the end. So now let's move on to our second puzzle. And I think this is really where it starts to get more creative as opposed to more math-based. Alright, so in this puzzle, Anna's trying to figure out how many children Bob has and what each of his children's ages are. So Bob's saying he has 3 kids. Let's call their ages A, B, and C. And 2 of them are twins. So we know that 2 of them are going to have equal ages. So let's just say C is equal to B. And the product of all of their ages is 36. So AB squared equals 36. And now Anna's saying she can't figure out all of Bob's kids' ages just from that information. And this is true because there are multiple different values of A and B, so that AB squared equals 36. Like, for example, A equals 36 and B equals 1 will work, and A equals 1, B equals 6 would also work. So Anna can't be certain which one of these cases it is. And there are also other cases too that I'm not mentioning yet. Now what Bob's saying is that he would tell Anna the sum of all three of their ages, A plus 2B, but Anna still wouldn't be able to figure out their individual ages. And then Anna's asking for more information, since she wouldn't be able to figure it out. Now, what Bob says here is really weird. He says, okay, my oldest child likes dogs. Then Anna's like, oh, now I know what all the ages are. And this does seem really weird. But let's try to start from the top. So we have that AB squared equals 36. And I've listed out two possible cases where this is true. But the other ones we can try to figure out are 9, 2. Because 9 times 2 is 18. Then 18 times 2 equals 36. And also 4, 3. Because 4 times 3 is 12. Then 12 times 3 is 36. And we can check that there's no more possible values of A and B using the prime factorization of 36, which is 2 squared times 3 squared. So the only square factors for B squared are going to be 1, using 2 squared, so 2, using 3 squared for 3, or using both of them for 6. Okay, so these are the possible values of A and B, and Anna's saying she can't figure out which one of them it is because she doesn't have enough information. Now after that, Bob says even if he tells her the sum of their three ages, she still wouldn't be able to figure out which it is. So let's think about this A plus 2B. So the sum of the ages, if one of them is 36 and the twins are 1, is going to be 38. Then here, we have the sum of the ages will be 1 plus 6 plus 6 equals 13. The sum of the ages here is going to be 9 plus 2 plus 2 equals 13. Then the sum of the ages here will be 4 plus 3 plus 3 equals 10. And we can see that Bob's saying, even if he tells her the sum, Anna still wouldn't be able to figure it out. But if the sum were one of 10 and 38, then Anna would be able to figure it out, since these two are the only cases where one of those are true. But if Bob tells her the sum of the ages is 13, these two cases are still possible, so she still wouldn't be able to figure it out. So now we've narrowed it down to these two cases, and Anna still can't figure it out. So then Anna asks for more information. And what Bob says is, my oldest child likes dogs. And after that, Anna's able to figure it out. So this is probably really weird, because what does my oldest child liking dogs have to do with anything? But what we can see is that he says, my oldest child. What this actually means is that his oldest child is going to be the one that's not a twin. Because if his twins were older than his other child, then he would be saying, one of my oldest children, since they have the same age. So we can see that in this case, the only child's age would be 1, then the twins' ages would be 6 and 6. Which isn't possible because this wouldn't be the oldest child then. And here, the oldest child has age 9, and the twins have age 2. Which satisfies this because the oldest child is not a twin. So now Anna knows that the ages of the children are 9, 2, and 2 from doing this type of reasoning. So now we have our final puzzle, which is way shorter than the other two and uses way less math, but I personally think it's the most creative out of all of them. So we have we're supposed to write down 5 odd digits that add up and make 14. Now, your first instinct after looking at this might be, how is this possible? If we have 5 odd numbers, odd plus odd plus odd plus odd plus odd, then any 2 odd numbers add to an even number, which means that this plus this is going to be even, plus this will be even, and then plus an odd number. Then an even number plus an odd number will be odd, so an even number plus an odd number will still be an odd number. But we're supposed to have 5 odd digits that add up to make 14, which is even. So how is it possible for an odd number to be an even number? And this isn't possible, clearly. So there's definitely something wrong here. So if we look at the problem again, what it says is write down 5 odd digits. But it doesn't necessarily specify that we have to have them in their same numbers, because digits and numbers aren't the same thing. So what we can do is write one number that has more than 1 odd digit. Let's say 2 odd digits here. And then we can use our other 3 odd digits to add. So then this will be 4 odd numbers, which are going to add to an even number. So now let's think about what kind of odd digits could add up to 14. Well, clearly this one must be a 1, because if it were 3, 5, 7, or 9, then it would be greater than 14, so adding these numbers would still make it greater. So now we have this 1, and then an odd number, plus these 3 odd numbers, equals 14. Then we can subtract 10 from each side. So this 1 and an odd number is actually equal to 10 plus an odd number. So after subtracting 10 from each side, we get that these 4 odd numbers are going to add up to 4. And then 4 odd digits that add up to 4 are just 1, 1, 1, and 1. So our final answer is 11, which is 2 1s, plus 1, our third one, plus 1, our fourth one, and then our last one, equals 14. So those were the solutions to our 3 number theory puzzles, and thank you for watching.